Hello, my name is Matthias Troyer. I want to talk today about utility scale quantum resource estimation. To remind you, we're aiming to build a utility scale quantum computer that is one that can solve problems where the value of solving the problem exceeds the cost. And the first question you ask, okay, what does that mean? How large a computer will I need for that? And that is the process of resource estimation. It is also done classically with a code profiler, with an architecture simulator. We can estimate the memory needed for a program, the runtime needed, the number of GPUs needed, or the software the developer can take a code and optimize it for a certain architecture. The chip designer may take a code and a profile, then optimize the new hardware for an application. All of this is done with a profiler and simulator, which is what we call the resource estimation. We do the same in the quantum case. We'd like to find out how many qubits are needed, what is the runtime, and what other parameters the machine needs to have. This may be used by many different people. The end user could be chemists. And those chemists may ask the question, what quantum computer is needed to simulate my chemical reaction? How many qubits will I need, and what will the runtime be? The system architect may ask questions of what are the algorithms I want to implement, what is the qubit type I want to choose, what is the quantum error-correcting code I want to employ. The quantum engineer will want to know trade-offs between qubit fidelity and speed and cost. And the way we do that is we have to find out what are the physical resources ultimately. The number of physical qubits, the runtime needed to run a certain application. So we have to go through the full stack from the application on top to the physical control signals at the bottom. That is again very similar in the classical case on the left and the quantum case on the right. We start with a program in the high-level language, we compile it down to an intermediate representation, and then to the executable written then in the instruction set of either the CPU or the quantum computer. Then within the CPU, the instructions are turned into microcode, and then into the control signals to the transistors. On the quantum side, the quantum instructions are turned into logical qubit operations, the physical operation, and then again into the control pulses sent to the qubits. The way we estimate the resources is we start with a program, we compile it, and although we don't have a scaled quantum computer yet, we can run it against a simulator and get a profile of the program. We can get the number of qubits the application needs and the runtime. And then I combine that with a model for the qubit performance and cost to get the final estimates. So let me walk you through that. And we start with our chemists. And the chemists want to know what are the properties of this ruthenium-based carbon fixation catalyst. And they ask the question, what are the resources I need to run that on a scaled quantum computer? And running the quantum program against the resource estimator tells them they will need 2,720 qubits for the application. It will take about 1 billion clock cycles to run it. They need an error rate of better than 10 to the minus 15 and about 1 billion t-states. Now that's where we see the first challenge. How do we get a qubit with an error rate of less than 10 to the minus 15? Physical qubits are always noisy. And that's why we use fault tolerance and logical qubits to improve the errors. So I'm using many noisy physical qubits to encode the quantum information in a protected way into a so-called logical qubits. Those logical qubits have an error rate that is lower than the physical one. And most codes have the parameter d, the code distance, that can vary to change the logical error rate. As I make the code distance larger, the logical error rate will get smaller and smaller. So now I have to choose a certain code and a certain code distance d to reach the 10 to the minus 15 errors. And that's where now things start to depend on the specifics of the machine or the code. So let us use an example, surface code for topological qubits. In this case, that's the equation here. These are the constants, and assuming a physical error rate of 10 to the minus 5, I can now estimate what code distance d do I need to get to the required logical error rate. Once I fix the code distance, there are equations that also tell me how many physical qubits I need now for logical qubits. In the specific case of the topological qubits with the surface code, it would be 4 times d squared. And it also tells me the time for a logical cycle. So now with that, we are almost there. We have the logical qubits I need for the application. But you also need to do the gate operations. And that's where most logical qubits can only do a subset of quantum gates natively, the so-called Clifford gates. These are basically in a single qubit on a Bloch sphere, rotations by 90 degrees. And that way can reach all the principal points on the axis. But the quantum program needs more. I need an arbitrary rotation gate as well. And that's where we face the next challenge, namely the arbitrary rotations are fundamentally analog. And we cannot correct analog operations. That's why in the classical world we have switched from analog computers to digital ones. We use 0 and 1 only, and not all the values in between. We face the same challenge here, and the solution is again similar. We approximate rotations through discrete rotations. And it turns out that in addition to the rotations by 90 degrees, the only other operation I need is a rotation by 45 degrees, the so-called T-gate. By combining rotations by 90 degrees and 45 degrees, I can approximate any near arbitrary rotation as well as I need to. If I have no T-gate, I can just reach the 6 points on the principal axis. With 5 T-gates, I reach many more, with 10 more, even with 15, 20. The more I use, I can approximate any rotation arbitrarily close. What is needed for that is this T-gate. And the problem once more is physical qubits are noisy. But I need to achieve an error rate of 10 to the minus 15 in our case. So how do I get there? The solution is a process called magic state distillation. While a single rotation by 45 degrees is noisy, what I can do is I can do many rotations by 45 degrees. In one scheme it might be 15. And then those many rotations can be distilled into a single one that's more accurate. And if needed, that process can be repeated in a second or a third round of distillation. So this way now, we know how to encode the quantum information into logical qubits. We know the overhead for this, and we know how to do all of the quantum gates. We can combine that to then get the final estimates, both for the physical qubit numbers and for the runtime. For the qubit numbers, we take the number of application qubits, multiply it with the cost for logical qubit, and we have to add in the number of qubits needed for distillation. In the example of topological qubits, that turns out to be about 1.2 million qubits. Similarly, we take the runtimes, the number of clock cycles, and multiply it with the clock cycle, which here gives us, for the 1 billion cycles, about 13 hours of runtime. With that, the user has the answer. The chemist now knows if they use a topological machine, they will need about 1 million qubits and the runtime will be 13 hours. They can redo the same calculation for superconducting qubits, ion trap qubits, neutral atoms, spin qubits, and find out what's needed there. They can then pick the machine that's best suited for the application. The system architect looked at multiple different QC codes and found out that for the qubit type he looks at, the best code is the surface code, and he wants to do 3 rounds of distillation for the magic T state. And the quantum engineer could explore the trade-off between qubit speed, fidelity, and cost, and learned that making the qubits 10 times better lets him reduce the qubit count by a factor 2. And he can now look at whether he wants to invest the engineering resource into making the qubits better, or whether he rather wants to invest the resources into building more qubits. Ultimately, we now understand what is the scale needed to reach utility scale, what are the qubit numbers, what are the runtimes we need to achieve that, and the coming episodes will discuss how that will impact the choices on the hardware side. Thank you.